Thanks for coming.
It's just bananas.
My name is Greg Cooper, and I would like to welcome you to this distinguished lecture in Causal Discovery, which is sponsored by the Center for Causal Discovery based here in Pittsburgh. I'm delighted to be able to introduce today our speaker, Dr. David Page. Dr. Page is professor in the Department of Biostatistics and Medical Informatics in the School of Medicine and Public Health at the University of Wisconsin-Madison. Before joining the faculty there in 1999, he completed his PhD in computer science from the University of Illinois Urbana-Champaign in 1993, and then did a postdoc in computation at Oxford University. Over the past 15 years or more, he's been at the forefront of research on machine learning in medicine and biomedicine. He has approximately 100 publications about this and related work. He served on NIH study section on biodata and management and analysis. Since 2003, he's been serving on the editorial boards of Machine Learning Journal and the Journal of Data Mining and Knowledge Discovery. He was chair of the 1998 Conference on Inductive Logic Programming, which within the field was still forming, and a lot of interesting things have gone on then and since then in that area. And he'll be talking about some more recent work in that area in his talk today. Dr. Page is a key member of the BD2K Center for Predictive Computational Phenotyping at the University of Wisconsin-Madison, which is one of the 12 NIH-funded Big Data to Knowledge Centers of Excellence that started last fall, that we are a part of. His current research is on algorithms for data mining and machine learning and their applications to biomedical data, especially clinical and high-throughput genetic and other molecular data. The subject of his talk today is machine learning for predictive phenotyping. His talk will include discussion of some work he's done on causal discovery in healthcare using statistical relational learning, which is of particular relevance to the work we're doing here and interested in doing in the Center for Causal Discovery. So please join me in welcoming our distinguished lecturer today, Dr. David Page.
Thank you so much, Greg, and thank you for having me here at one of the world's top places in biomedical informatics. Really is a pleasure to be here with you today. Please stop me at any point if you have questions. I want to start with acknowledgments, just because if you stop me a lot with questions, which I hope you do, I may not get to my last slide, so I want to go ahead and get that in right now. Thanks to funding agencies. In particular, I'll talk about some work with the International Warfarin Pharmacogenetics Consortium and the Wisconsin Genomics Initiative, and especially a number of collaborators, students that I've had, but also a number of collaborators at the Marshfield Clinic. So Marshfield Clinic, for those who don't know, had one of the world's first electronic health record systems going back to the 60s for diagnoses, and then added on. They still have their own homegrown system. They also have one of the world's first DNA biobanks, where they have about 20,000 patients in their personalized medicine research program. So Marshfield Clinic's resources enabled, in terms of data, especially enabled a lot of this work. So many of you heard either President Obama's State of the Union address or his press conference on precision medicine or personalized medicine. And so this is a view that I think a lot of you have, a lot of us have, for what we'd like to see with personalized medicine or precision medicine. And I want to start over here. Whoops, am I going to mess up? I think I'm messing something up. Let me use this pointer instead. Okay. So I want to start with this vertical column over here, that our goal is when a patient comes in, and we may have eventually detailed genetic data on this patient. Now that, depending on your definition, we're at or near the $1,000 genome mark. Clinical history data, and maybe even environmental exposure data on this patient. We'd really like to do things like, when we make a diagnosis for this patient, to say that of the 3 possible treatments, this one treatment, the patient is at an elevated risk compared to the rest of the population for an adverse reaction. So we don't want to give the patient treatment A. And of treatments B and C, our prediction is the patient will respond better to treatment C. And we'd like to be able to make that determination. Or we'd like to be able to say, or maybe even have the electronic health records, the doctor's typing, the clinician's typing into it while she's talking to the patient. We'd like the system to maybe pop up. Did you know that the patient in front of you is at an increased risk of a stroke in the next year or a heart attack? And we'd like to be able to take an earlier action in order to prevent that undesirable event. So in order to do that, we really need to have at this step predictive models for a number of diagnoses, a number of potential future procedures, a number of treatment responses. And we'd like to be able to use those predictive models in order to make more personalized treatment decisions. Now, many people would say, all along we've been making personalized treatment decisions, but more precise decisions, and that's where the name precision medicine comes from. Well, how do we do that? Well, as we've gone to a world and a country now where we have more than half the patients having their data, clinical data, in electronic health records, and as we've said, more and more availability of genomic data, and we see what happens to these patients over time as they age, as they progress, contract certain diseases, as they get certain treatments, and we see how they respond. This makes a fabulous data set and data source for machine learning. So we'd really like to be able to run all of these patients on whom we have data through our various machine learning algorithms, build these predictive models that we can then use for many thousands of patients as they come through. So that's the big picture vision. My challenge today is I want to give a big picture vision talk, but also get into the details of some of the algorithms, and we'll see how time goes with that. But I'd like to try to do both of these things. And so a patient comes in, and we have some basic demographic information on the patient. The patient comes in, and some signs or symptoms, I've got a bad break there on symptoms, but are recorded maybe in natural language, maybe in a coded form, and a diagnosis or more than one diagnosis is recorded in coded form. Patient comes in the next doctor's visit, and there might be another diagnosis recorded. It may be another occurrence of the same event, such as atrial fibrillation, the most common form of heart arrhythmia. And we'd really like to be able to predict what's this patient going to have the next time they come in, and when are they going to be coming in next. Because if that's something very serious, we'd like to know if maybe there's some action we can take now in order to avoid this. So the electronic health record, I know many of you are working with this type of data, but for those who maybe aren't, this is a slightly simplified version, but the coded data, apart from the natural language text, looks like a table for demographics, a table for ICD-9, soon to be ICD-10 coded diagnoses, symptoms maybe in natural language text or maybe coded, lab results, vitals, medications, also for space reasons I'm not showing a few other tables that we commonly use like CPT coded procedures. And eventually, on some patients now, but hopefully soon on many patients, genetic data, either SNPs or single nucleotide polymorphisms, individual positions where people vary, or hopefully in the not too distant future, whole genome sequences on everyone who's interested in having that. Now this is, as you can see, a relational database, but most of our machine learning algorithms assume the data are in a single table, basically an Excel spreadsheet like this. And then we pick one particular field or column that we'd like to predict in terms of all the other fields, using maybe a decision tree learning algorithm, a random forest learning algorithm, a support vector machine, and even a number of other algorithms. I think most of you are already familiar with many of these, so I'm not going to include slides here giving the details of these, but these are all algorithms that can build predictors, typically with a probability of prediction attached, for one field or one column, given all the other columns. And yet, nevertheless, the data is in this relational database where to squash it into the single table field, we typically lose information. Or if we don't want to lose information, we do a massive join where we change radically the frequencies in the data on which these algorithms, these machine learning algorithms critically depend. And even then with a join, we really don't have the data in the format we want where we have one row per patient and all the columns neatly aligned, because one patient may have 5 different doctor visits in the last 10 years, and another may have 100. And how do we align that kind of data? It's analogous to the kind of problem we have aligning sequence data when different people can have somewhat different lengths of sequences owing to insertions and deletions. So these are some of the challenges, and typically we will work with data in this format where we'll create features like for every diagnosis code. How many times has the patient had that code in the last 1 year, 3 years, 5 years, ever? Same thing for every procedure, same thing for every lab, except there we may need to aggregate, like with max, min, and mean, various aggregation functions. We'll often work with the data in this form, but we'd like sometimes to work with it in its more native form, either as a relational database, or with each patient, I'll say more about this soon, with each patient as a timeline of events that occur over time. But regardless of the representation, whether it's the one I just showed or one of these other representations, the basic specification for what we'd like to do is, given the values for a bunch of features like diagnoses over time, labs, vitals, we want to build a model that can accurately predict for patients where the value is unknown, one of these particular fields of interest, like heart attack in the next 5 years or myocardial infarction in the next 5 years. Okay, so we sometimes call this predictive phenotyping because an event like having a myocardial infarction can be thought of as a physical manifestation of what's going on with that patient. There are genetic factors, other factors that might feed into that, but in contrast to a genotype, we may think of that as a phenotype. And so this vision that many of us have is really doing predictive phenotyping. When I first got involved with electronic health record data about a dozen years ago, I had come from working with machine learning applications to a number of other data types, including molecular data. And I thought, well, this is going to be really easy because whatever I want to predict, like myocardial infarction, there's a code for it. And I just look and see, did the patient have that code? And silly me to think things would be so easy, even in really clean, carefully monitored electronic health records. That record's being used for things other than just to make my life easy. It's being used for things like, among others, billing. And so it may be that the doctor needs to bill for a test to see if the patient did have a myocardial infarction. So they need to test troponin levels or other things. And that code for myocardial infarction gets entered to justify the test and doesn't get retracted once it's determined the patient didn't have VMI. So that's just one of many reasons we might have a kind of noise in this data. And that gives rise to a task of just doing explanatory or retrospective phenotyping. Who did have a heart attack or who did have atrial fibrillation? And that in itself is a challenging task. And so I want to talk about machine learning applications for both of these tasks today, because I started with predictive phenotyping. I'll actually start with that as I go through some case studies and algorithms, then come back to explanatory phenotyping. And then another point that we're really interested in is not only accurately predicting who will have a heart attack in the next 5 years, but we'd like to avoid that, obviously. So we'd like to say, gee, if I get the patient to stop smoking, or if I could change other variables in this patient's data, how much would that change the risk? How much would that change the probability of heart attack? And for that to happen, an accurate predictive model is not enough. We need a causally faithful model. So for a number of applications, we need to address causality and causal discovery, and so we'll come back to this issue. We'll start here with predictive phenotyping, and I'll start with one particular case near and dear to my heart from Wisconsin, which is Warfarin Orphans, a widely used blood thinner, in part widely used because you can take it by mouth rather than hook it up to an IV. And there are some newer generation blood thinners being used now, but Warfarin was originally discovered, some of you may know the story, as it was presented to me in a simplified form when I moved to Wisconsin. One of the dairy farmers in the northern part of the state, like in the 1940s, his cattle were dying. He didn't know why, so he loaded up a cow on the back of his truck and brought it to the biochemistry department and says, you know, you're here to serve the state of Wisconsin, figure out why my cattle are dying. And so I think it sat in the freezer for about a year, and then a really bright biochemist looked at this and finally isolated the compound that was causing the cattle to hemorrhage to death. And it was it was a molecule coming from a fungus growing on the clover that the cattle were eating. And so it was originally marketed as a rat poison. It's named for the Wisconsin Alumni Research Foundation, our patenting arm. And then somebody thought it'd be great to give this to people. And as you can imagine, there are problems that ensued, in part because the dose for different people varies quite widely, depending in part on things like like your height and weight and gender, but also in part on some key genetic variations, and in part on diet and smoking and other factors like that. So a number of people for many years have been interested in predicting what's called the stable dose of warfarin. So it's very common to start people on 5 milligrams a day, vary the dose, but as I understand it, warfarin has its peak effect 4 days after you take it, so you're measuring this INR, or international normalized ratio, degree to which the blood is being thinned. You're measuring that regularly and adjusting the dose, in some cases even before you've seen the peak effect of the last adjustment. So it makes sense that if you could predict the stable dose for a patient and start the patient at a better initial dose, then you can make things safer for the patient. Warfarin, I think, remains in the top 10 overall for drugs with adverse drug events. So as people built models for this, they realized that their models were radically different, and their models made radically different predictions for individual patients. And that was obviously a big concern. So a number of different research groups from all over the world got together and said, let's pool our data and see if we can build a better predictive model. So these sites that pooled their data ran into the issue that at every site there were people who wanted to do data mining, machine learning, statistical predictions, regression, and try to build predictors. And this was where I got brought in. This was very fortuitous for me. I had recently run a KDD Cup competition before this, focused on healthcare-related predictions. And so basically, I ran this analysis piece of the IWPC's work as a competition. I said, okay, here are going to be the same folds for 10-fold cross-validation. We're all going to use, there's going to be a separate 20% of the data held out for validation, and we'll only touch that after we've committed to one particular model that we're going to use. And so these are a few slides from the IWPC, just showing that as I've described, warfarin dose, so I said 5 milligrams a day is a typical starting point, so 35 milligrams a week you can see here. As it's showing, the dose varies quite a lot with age, height, weight, and you really only know the right dose for the patient after they've gone through this dangerous time where their dose is being adjusted until you get the INR in the target range, typically 2 to 3. You also see the dose varying with race, with use of other types of drugs, enzyme inducers and amiodarone. You see how it varies with genotype. In particular, 2 genes, CYP2C9 is involved in metabolism of this and a number of other drugs. VCORC1, which is color-coded rather than coded by position on the x-axis, is involved in the vitamin K pathway, which is the pathway on which warfarin, we now know, acts. And so you can see variation with genetics. And so when we got through dividing up the data, we had a validation cohort of about 1,000 patients, a training set of about 4,000 patients. Within this set, we did 10-fold cross-validation with the same folds as the method for the competition to see which method worked the best. And I was very excited because initially, support vector machines, in fact, nonlinear support vector machines, were working the best on this task. And I was very excited about that as a machine learning researcher. Interestingly, a number of the clinicians were very concerned about that because they didn't understand how the method worked. And not only that, but it can be hard, especially with a nonlinear SVM method, to understand exactly how the predictions are being made. Linear SVMs were performing roughly equivalently, and so they're easier to understand. You can basically look at a coefficient or weight on each individual feature. In the end, though, an ordinary least squares linear regression model performed just as well in the 10-fold cross-validation, and the clinicians liked that a lot better, so that was the one we took. I was disappointed as a machine learning researcher, but that was the one we took to the validation. This is the model actually shown, so you see the same variables that we were just talking about. And you see that this is significantly lower error, this is the model I'm talking about, than the fixed 5 milligrams a day. There was also the interesting question of how much genetics were helping. And you can see they're helping some, but the bigger gain is just using a predictive model. And interestingly, in a couple of recent clinical trials, it was found that even though the error rates look like this, when you do a predictive model rather than fixed 5 milligrams a day, you do get significantly better outcomes in terms of health. But the genetics, at least in this one clinical trial that's been done so far, the COAG study, the genetics did not significantly improve outcomes between just using a predictive model without genetics. But there's still a lot of further study and further room for study on that issue. Yes?
A very quick question.
Yeah.
So you did this with the square root of dose, is that right?
That's right.
And it was on a free parameter, or was that those are just?
So you're going back and taking this model, and then you're squaring the output of the model to make your final decision. And experiments were done with square root of dose, log of dose, and just using the dose itself. But with the free parameter, you meant the square root. Was that a free parameter? No. So that was just decisions that different people made in their modeling. Those were the only 3 that were tried. And this was before we went to the final validation cohort. So it was a fair evaluation, but maybe there's room to make it better by choosing a different exponent there, or some other transform. So square root and log transforms are pretty common transforms, but maybe you could do better by trying that. Thank you. Other questions? So that was interesting, an interesting experience, a little disappointing to me in that ordinary least squares regression did as well as anything else, but potential for significant clinical impact there. A related task that we've also looked at is adverse drug events of various types. Here we did a study with COX-2 inhibitors, so some of you are familiar with these. They were very wide-selling drugs, and then it was found, not in clinical trials, but after the drugs were on the market, that some of these, in fact, all of them to some extent, but especially Vioxx and Bextra, doubled the risk of heart attack. Celebrex is a less extreme case. It's still on the market with a warning attached to the label. But this raised the interesting question of looking retrospectively at the day someone was prescribed a COX-2 inhibitor like Vioxx, how accurately could we have predicted who would go on and suffer a heart attack or myocardial infarction or an MI? And in fact, so this is showing ROC curve just for 3 different methods on this task with Marshfield data. And I want to talk just a little bit about the method in blue because it's an algorithm that, unlike these other 2, doesn't convert the data into this single table or feature vector representation that's so common, but works directly with it in its relational database form. And so we're going to veer off and talk about algorithms for a little while and then come back to some big picture applications issues. But several times today in the talk, we'll take I don't want to call it a detour, but we'll take a drill down and look more closely at some of these algorithms. Okay, so I mentioned earlier that you can also think of a patient as a timeline. So this is time going forward, the patient's clinical history. Maybe you have a medication given at a particular date. You have the patient's some basic information about the patient, such as weight here at another measured at another date. Notice there's a lot of missing information, so we don't know continuously what the patient's weight is. And we don't know continuously what over-the-counter drugs the patient might be taking or what events the patient experiences. We only know things that are significant enough that the patient comes into the clinic. And the patients don't conveniently come in every week in lockstep for us to measure all the same things. So this is the challenge in the data. This is just one particular type of drug. And we might be interested in, well, is there some adverse reaction to this drug that's going to occur in the future? So we could do this. We did this with the COX-2 inhibitors. We looked at this with a number of other drugs. And these are in cases where there's a known adverse event. And we're just trying to predict who would experience that adverse event. So the big picture approach that we're taking here with the relational data, if we want to run a standard feature vector algorithm or algorithms that assumes a single table, then we have a gap between the form of the data and the algorithm. And one approach that might be very natural here, because we like probabilities of adverse events, is a Bayesian network. I'm showing a particularly convenient form of Bayesian network here, where the adverse drug reaction or adverse drug event is a class variable. And the other features, the other variables, are basically, if you ignore these arcs down here and just take these arcs, this is the form some of you may be familiar with as a naive Bayes net that would assume each of these features is conditionally independent of the others, given the class node. But you run into problems that if these are very associated with each other, say in the extreme case they're redundant, then in a way you're overcounting them. And there can be other types of correlations or interactions between these features. And you like to pick up on the strongest of those. And so TAN gives you a way of doing that so that you get the maximum likelihood structure that fits the TAN constraint, which is if we now ignore these arcs and just look down here, we have a directed tree on the features in addition to our naive Bayes arcs. Now, the other twist, though, that we're making to a TAN or tree-augmented naive Bayes representation here is that we're going to learn these rules, and they are going to be our features. So you could think of this in a way as a first machine learning step to decide what the features are or to convert automatically to this flat file or this feature vector representation. And so these features are rules that are equivalent to SQL queries that might say things like a patient P is at risk of this particular adverse drug reaction if patient P goes on this drug and they have a particular weight, so a weight underneath 120. And you could string together more of these literals or more of these components, these preconditions, to make a more complex model. Like you might say, if the patient's on another drug, and the patient started that other drug more than 2 years ago, so they've been on it a long time. And so you can get temporal relationships. If you have the data, you can even incorporate data on family members. The patient has a mother who had some incident, some health-related incident 10 years ago, something like that. So anything you could represent with a SQL query over your database, you can represent equivalently in the form of one of these logical rules. And early approaches to try to combine something like Bayes nets with these logical rules would first run a standard rule learning algorithm where it's trying to optimize something like information gain or accuracy of the rule, or precision and recall of the rule, some function of those, maybe F1. And instead, we took a more integrated approach where we said, let's try lots of rules, but we'll score a given rule by how much it helps our current Bayes net. And then the other piece of this I won't go into details about is it turns out you can modify the TAN algorithm really easily to be incremental so that I don't have to retrain the whole TAN network when I add just this one additional feature. I can do that incrementally very quickly. And so essentially what's happening is we're searching a space of candidate rules that you could build, SQL queries that you could build over your representation, and we'll test how much the rule helps our model when it gets added to the current model on a separate tuning set. And typically we measure score by area under precision recall curve, or some of you may know that as essentially equivalently mean average precision. But you could use area under an ROC curve or just straight up accuracy. And you keep doing this as long as you can improve on the performance. That was the method that we used for the COX-2 inhibitor case that I just showed you. One interesting problem that crops up, though, is that, again, I said that the electronic health record wasn't created for us in order to make our lives easy. It was created for very other reasons. And so often the data that's available for us to make a discovery is not necessarily at the right granularity for us. So a particular type of drug may get refined down to several different specific drugs of that type. And what's important may be the specific drug or the drug category. Worse yet, you get many different formulations. And so even a particular drug may get broken down into many different representations. Similarly, the same thing occurs with diagnoses. And so an approach that we took was to do a kind of clustering, but not just a general clustering, but a task-specific clustering. So once we build a rule, we would ask, gee, are there other drugs, or if it were a condition, are there other conditions that we could cluster together in here and improve the overall performance of the rule? So in parallel, you're learning a cluster of drugs and modifying your rule. You could also just use known existing hierarchies of diagnoses and drugs. And so we tried that as a point of comparison. And I apologize, I haven't had time to go through all these algorithms, but the gist is that this is the new algorithm with the clustering. These are variants on the original algorithm, and the Expert Plus is including the standard hierarchies on drugs and conditions. And so you can see for COX-2 inhibitors, for warfarin, and less so with ACE inhibitors and angioedema. This is warfarin and bleeding, ACE inhibitors, angioedema, COX-2 inhibitors, and heart attack. That the new method, with or without the extra expert input, never hurts us, but often helps us substantially in terms of our area under the PR curve. Okay, so hopping back up to a high level from specific algorithms and approaches, we've applied the same kind of approach. Oh, sorry. Yeah, thank you.
You're cruising along pretty quick.
I'm sorry. Yeah, no, thank you.
So just two quick questions. The reason why you guys are using math, is that because you can't get the true negatives in this situation? So what's the reason for choosing that area under the precision recall curve?
Okay, well, we actually choose area under the precision recall curve because we are, in most of these cases, I'll cite some counterexamples a little bit, but in most of these cases, we are trying to use a natural kind of case to control or positive example to negative example ratio. And that's especially a big issue in this next topic I'm going to come to, which is mammography. So mammography has been in the news a lot recently in the last few years because you can get these great ROC curves that look like you're right up near ROC heaven. And yet ROC, the good and the bad thing about ROC representation in evaluation is that they're treating your positive examples as having a sum weight equal to your negative examples, even if you have far more negative examples. And so, so even though you have this great ROC curve, if you plot this in precision recall space, because thankfully most abnormalities on a mammogram are benign rather than malignant, if you plot this on a precision recall curve, where recall's here, precision's here, you end up, by the time you're at the 0.9 recall, where you'd like to be operating, your precision is down around 0.1 or even lower. And so many people have this experience that when a woman gets called back for follow-up to abnormality on a mammogram, there's less than a 10% probability that really is a malignancy. And so there's concern over overdiagnosis, too many biopsies, unnecessary biopsies, and even over treatment, because of the issue that many of these also don't need the treatment necessarily, even if they are a malignancy. And so that brings us back to this point that for many of these, if you really are using the natural case control ratio out there in the world, area under an ROC curve or overall accuracy can be very misleading compared to area under a precision recall curve. So that's why we use AUCPR. But the method could work with any of it.
That makes good sense. So when we talked about it in the information retrieval class, we do talk about the need to have the inability to use the ROC curve. And then in machine learning in the clinical setting, it sounds like the use of precision, you have a more direct sort of mapping. So how often would this thing fire?
Right.
And the person would have to say, oh my gosh, I got to act on this.
Right. It'll very often be, we're going to take this sensitivity, like 0.9, and what's our positive predictive value or precision when we, if we're at this given sensitivity or recall.
I was confused though in your slide when you on the slide it said there was no medication hierarchy.
Oh, there are medication. No, I misspoke. The slide said that there are several medication hierarchies, but there's not, to my knowledge, one gold standard medication hierarchy like there is the ICD-9 hierarchy. There are medication hierarchies based on pathways targeted, or based on class of drugs, or based on what the drug is being given for. So there are several. So you could build one big medication hierarchy, but there wasn't one as convenient. So I think what the slide was saying, for purposes of this experiment, we just used the diagnosis hierarchy.
Okay.
Yeah. Thank you. So thank you for those questions. I apologize for going a little too quickly. Other questions?
So just
yeah.
You guys should probably talk down the road because Richard's very involved with the OMOP model.
Oh, fantastic!
He's a rich phenotype exploratory framework. So I just wanted to give you a plug, Richard.
I'd love to talk. I'd love to talk more about, since you mentioned information retrieval, I'd love to talk more too about PR curves. I had another graduate student who showed, well, in fact, this same student, Jesse Davis, showed that there's a direct mapping, assuming you're dealing with a particular data set with a particular number of actual positives and negatives. There's a mapping that will take you back and forth between ROC and PR space. And there's some interesting properties that follow from that, that even though one method could be better than another in area and worse in area under ROC and better and then worse under area under PR curve, if you dominate in one space, you dominate in the other. And I had another student who showed that that PR curves can be very misleading in some cases because of some properties that have to do with this mapping and because of the relationship to your class skew. So I'd love to talk about some of that. So those are issues that come into these scoring functions in quite a big way. So this very same SAYU is the same algorithm I was giving you before, and this is an approach where we're taking the same algorithm and applying it to data in the National Mammography Database Standard Framework that radiologists were entering. So we're not looking at the images, but we're looking at data that they're already entering. And this is the radiologist performance, and we're significantly improving over the radiologist performance. But again, this is in ROC space. In PR space, though, you see a significant improvement that's right in the region where you'd like to operate, the high recall region. So we've continued to apply this method that's tailored to relational databases to a number of these EHR-based tasks. I'm going to have to skip a few things because I want to get to the causal inference part. But I just want to say that briefly, there's also been a lot of interest in genome-wide association studies and GWAS for breast cancer and a number of other diseases. And GWAS results many people have said they've been kind of underwhelming. They haven't told us as much as we hoped they would. And many of us hope that when we get whole genome sequence and epigenetic data and things like this, that we'll see maybe more signal there. But I want to zoom into the same mammography task. And here's an ROC curve and a precision recall curve. And you can see from this ROC curve, this is a much more challenging group of patients. These are specifically patients that went all the way to biopsy. So we know ground truth. And so the positive examples here are all false positives for the clinicians because they went to biopsy. And in this group, what I want to focus in on is the black dotted line, which is the performance of the radiologist. The green line, which is performance of a model akin to the model we just showed you. And you remember it had a very good performance in terms of ROC space. And now we've added genetics, which is just predisposition information. This is just the patient's germline genetics, not from a biopsy sample. So this is something you could do before going to biopsy. And here, we've really just added to a Bayesian network one new feature that's a count of the risky alleles or the high-risk alleles in all the SNPs that have been published in GWAS up to a year ago, which was 77. And you see that you get actually a pretty substantial improvement with this predisposition information in this region where you'd like to operate, roughly the 90% sensitivity or recall region. Okay. And then finally, to finish off the predictive phenotyping part, before I go on to causality and maybe a bit about retrospective phenotyping, I just want to say that this is kind of back to the Warfarin story, that for all my trumpeting of the benefits of relational learning and statistical relational learning, where you combine a statistical model like a Bayes net with a relational learner, very often just squashing things into one feature vector and running random forest works incredibly well and frustratingly well. And so we also do plenty of that. And so this is looking at that approach with atrial fibrillation or flutter, and then asking, given atrial fibrillation or flutter, 1 year, 3-year mortality, and stroke, where the risk of these is increased. We were really shocked that we could predict AFF this accurately from clinical history alone, but that we could predict stroke this poorly. We felt it would be very much reversed. And so we're continuing to look at ways to predict this more accurately. Okay, I'm going to just briefly make this point that I said in addition to looking at a patient as an entry, as an entity in a relational database whose data is spread over multiple tables with potentially many entries in any one table, like many diagnoses, patients are often naturally thought of as timelines as well. And we've done work in the past where we tried to do causal discovery from temporal data, just purely observational data, in molecular settings where we use dynamic Bayes nets. And so, so going back to, I think, 2002, we were doing dynamic Bayes net learning from gene expression data, and other people were looking at this as well. And the nice thing there was you had nice regular time points at which everything was measured. Now you had to worry about whether the time points were the right ones, whether you were measuring with the right frequency, but at least they were nice and regular, the same stuff being measured at every time point. Here the patients come in when they want to come in, so the data are very irregularly sampled. And so I just want to briefly say that I think there's a lot of promise in applying point process methods and continuous time Bayes nets, methods that are tailored to this sort of timeline data, which is what I'm calling the irregularly sampled temporal data. There's a lot of promise in these for some of these methods. And so we've been doing some work on improved machine learning algorithms for learning the structure of CTBNs or point process models. But I'm going to jump ahead over some of this. This is just giving you the gist of the method, that the sufficient statistics you're interested in when you're doing parameter learning are really just the counts of transitions and time duration in particular states. But let me jump ahead and say that essentially what you're getting looks a lot like a Bayes net, except you're allowed cycles now, because you're saying, depending on the parents of this node, say it's your HDL level, depending on the parents of this node, you have some intensity for transitioning from normal to high, or transitioning to a different value for this variable. So in order to get onto the causality piece, and the causal inference piece, I'm just going to say, big picture, our lessons from the predictive phenotyping so far have been that timeline modeling that I just showed you is appropriate, but we really hit big issues in runtime, especially because with CTBNs, because we have to deal with the fact that so much of what's going on for this patient is missing. And CTBNs expect that you have full knowledge of the full trajectory of the patient's values for all of the variables. I think these are promising, but there are a lot of challenges that remain. Another big lesson that we've had, whatever the machine learning approach, is that it's kind of disappointing, but most of the time, genetics don't help us a whole lot with our predictive accuracy. Warfarin was an exception, and that breast cancer slide I showed you was an exception, and age-related macular degeneration is another exception. But everything else we've done, if you have the whole clinical history, then the genetics really doesn't up your area under the ROC curve, area under the PR curve at all, which has been sort of disappointing. So our hope is that maybe with more detailed data on genetics, that story will change. With a few very carefully clinician-selected features, ordinary least squares or logistic regression often perform the best, but you can almost always do better by throwing in everything and applying either a relational learning technique or, in many cases, good old random forests. So with that, I'm going to jump ahead. I think I'll jump ahead to the causal inference piece, but let me see if anybody has some questions. So this next, well, okay, let me just briefly say, big picture, my vision, and I think other people share this vision, and we're starting to act on this now at Wisconsin. You know, I'm a computer scientist, so I like to automate things, and so I was telling Greg and Mike and Mike last night that we really want to try to build a predictive model for everything. Now, I'm not optimistic enough or overconfident enough to think those will all be accurate predictive models. But we'd like for every diagnosis code, and we're doing this now, and eventually for every procedure code and every treatment response, we'd like to see how well we can predict that from large numbers of patients and cherry pick the best of those, the few that are really highly accurate, and try to start translating those into the clinic. And so we're very excited about trying to do this going forward. I mentioned explanatory phenotyping or retrospective phenotyping. This is a fascinating topic where Peggy Peissig at Marshfield has made some big contributions. Vanderbilt, Josh Denny, and others have done some neat work using machine learning for this task. The specific angle on Peggy's work is that she's trying to learn these same kind of rules that many people get from working with clinicians using the kind of techniques we've already talked about, use these same kind of rules to learn retrospective phenotypes. This is just showing you some issues to do with the EHR data and challenges in the EHR data. So if you'll bear with me, I'm talking about how phenotyping is usually done with clinician input, and our clinicians are driving us to leave them out of the loop in all of this work. And so I want to jump ahead to Peggy's results briefly, which are that with the relational learning approaches that you see here, you often see benefits over the standard feature vector machine learning approaches for this kind of retrospective phenotyping across acute MI, acute liver injury, atrial fibrillation, cataracts, across a number of different phenotypes. So I want to jump now to the causal discovery piece. So as I said earlier, you'd really like your model to be causally faithful so that you can propose changes that you might make in a patient's care or in patient's activities and lifestyle in order to improve the predicted outcome for the patient. And the task that really drove me to say, gee, I'm nowhere near somebody like, an expert like Greg Cooper for causal discovery, but we've got to address this somehow, is this adverse drug event task. Adverse drug events, of course, we know are a huge problem, but the task that we're interested in here is really the OMOP task, the Observational Medical Outcomes Partnership task. It's not this first one I talked about earlier, where we already know the ADE and we want to predict who will experience that. It's where we have a specific drug and we don't know if it's causing an adverse drug event or adverse drug reaction, and we'd like to figure out if it is. And so OMOP, for example, had this matrix of drug categories and health outcomes of interest. And they had shown in red are cases where you knew from the drug label that the drug could cause that particular health outcome of interest. Nicely worded. In a few cases, you knew that the drug could help prevent that outcome. That's shown in green. Everything that's not red or green is a not known adverse event, and so the blue ones were drawn to be negative examples of adverse drug events. And so that was the OMOP task, was to say what kind of mean average precision or area under the ROC curve, they looked at both of these, could you get at recovering these adverse drug event, the drug condition pairs that are in red compared to those that are in blue. So another way to look at this is we have a bunch of drugs on the left, a bunch of conditions on the right, and we want to try to match them up. And how accurately can we match them up? But the OMOP task, and I'll say more about results on the OMOP task in a minute, it's a terrific resource, and there's several variations of their evaluation that they've produced now. But we think, despite all the great work that's been done evaluating different methodologies like propensity scoring, self-controlled studies, and many others on this kind of data, that there's another important extension besides just extending to more drugs and more conditions. So let me just jump ahead and say, instead of this being what we want to address, we want to address this problem, where we have the list of drugs and we have the EHR and nothing else, and we don't know what condition the drug might be causing. And what we'd really like to do, going back to this kind of relational database learning, is we'd really like to be able to learn a rule like COX-2 inhibitors. If a patient P takes a drug D that's a COX-2 inhibitor, what might it cause? Well, maybe it causes hypertension. But in general, if you look at the data, you don't see strong evidence for that. But if you zero in on hypertension in patients older than 55, and when the drug in particular is Vioxx, then all of a sudden you do see very strong evidence for that. And you'd like to be able to discover that from the EHR without somebody giving you this brilliant insight ahead of time to look for that in particular. And so that's something that the OMOP task did not specifically address. So can we discover really unknown or unpreconceived notions of adverse events? Well, the problem we have here is in standard machine learning, we're good at cases where we know this thing on the right and we want to figure out this thing on the left in order to predict it, or we're pretty good at that. But in this case, you don't know the thing on the right. So how could you apply some kind of machine learning to that? Well, our approach was to take the same relational learning algorithms that I've already talked about and use them in reverse of the causal direction. So to say, we know the people who were on the drug and who weren't. That's the only thing we really know besides in general what's on in the EHR. So let's just take that knowledge and ask, can we predict who was on the drug based on things that happened after they went on the drug? And so another way to think about this is you're using patients as their own controls, which is a great older idea from epidemiology. And so you're saying my positive examples are going to be patients after they went on the drug. And negative examples, some of those will be the same patients before they went on the drug. So we're, in some ways, partially at least, adjusting for unmeasured confounders. You and I were talking about this before because we don't know what it might be about this patient that could be confounding the matter, but if we're using the same patient, we can adjust for that in part without even knowing. And so these were some of the rules that we learned from this that in fact were things that were supported in the literature afterwards. And in addition, we found the rule that I showed you earlier in that illustration with hypertension in older patients on Vioxx. So these were some of the things that we learned, but we were only able to learn them after we made a critical change to our relational learning. So instead of using the relational learning algorithm as it was at the outset, which is using a kind of correlation-based score, in a sense would be correlating conditions that we might build with the drugs, that's completely uninformative. Instead, we changed the scoring function to be among those patients who had the condition and the drug, what fraction of those patients had the condition after the drug, time of condition after time of the drug. So we focused then on temporal ordering. And then some conditions just happen later in life and follow lots of drugs. So the capital C represents taking this over many different conditions, the capital D over many different drugs, and normalizing by them. And when we do that, it's anecdotally, I can show you we uncovered some nice rules. We also uncovered some lousy rules that looked like they were still capturing, even though we were doing this self-controlled approach, they looked like they were still capturing indications or reasons people went on the drug. That's all anecdotal evidence. So we also took the same approach. Let me just jump ahead. And it's the same what I already told you. But let me just jump ahead and say we also took this approach and did apply it to the OMOP discovery task. And whereas the correlation-based scoring function gave us nothing, we basically tracked random guessing. Now we're competitive, at least, with a number of other methods for the OMOP rediscovery task. But the method scales up to these kind of unknown or unanticipated preconditions. So this is still very much work in progress. But we asked ourselves the question, I just got just a few slides left. We asked ourselves the question, why are we and others still only at ballpark 0.75 area under the ROC curve? Why can't we do better? And we think this is clearly, when we look at the results, it's clearly because of measured and probably unmeasured confounding. And so in particular, if I look here, we had this problem I mentioned earlier that ACE inhibitors cause angioedema, but scoring better than that was this wrong connection of ACE inhibitors to bleeding. And we think the reason is if you built a graphical model, whether it's a Bayes net or an undirected model like a Markov net, there are other paths through which information can flow in certain circumstances between ACE inhibitors and bleeding. such as people are on ACE inhibitors because they have hypertension and also increased risk of MI and stroke. I'm not showing everything here. And therefore, a fair number of them might be on warfarin as well, which causes bleeding. And so Aubrey Bernard, my graduate student, is working on an approach now where we feel like we don't know enough to build this model ahead of time that we would need. So where he's trying to learn a graphical model, in his case, he's learning an undirected network, a Markov network. And when you do the weight learning in the Markov network, what essentially happens now is instead of all the weight going on this, or sorry, this is the offending edge. Instead of all the weight going on this edge, you get it distributed because a lot of that weight goes on these other paths that can connect ACE inhibitors and bleeding when you're doing the Markov network weight learning. But the one big problem is the standard Markov network approach is based on statistics and correlation. And so Aubrey had to modify this to be based on time. And so the weight is essentially, in every case, on this preceding this consistently in time, or this preceding this. And so we found that easier to do with a log linear formulation of Markov networks with precedes or before features for which you're learning the weights. And these are just, I can come back to these if you ask me questions, but this is an ensemble of the earlier approach I showed you together with the Markov network approach. And you can see that the ensemble is competitive, at least, with the best of the current methods from OMOP across a variety of the different OMOP data sets that OMOP makes available. So this is still very much continuing work. We need better ways to do inference in these undirected models or Markov networks so that we can put more variables in here, and we need better ways to deal with the unmeasured confounders, potentially proposing new variables, for example, from the relational learning. So I need to wrap up quickly. I just want to jump ahead to say other challenges that we feel like we face in precision medicine include, among others, better ways to do GWAS, or in the near future, hopefully, whole genome sequence data analysis, and privacy, better ways to deal with privacy. So one quick slide on each of these. We went back to the IWPC data set, and Matt Fredrickson really led this work. He's finishing up now with Somesh Jha. Matt showed that you could use differential privacy, which in a sense adds noise to the data to protect against any one patient's information being given away when you, say, ship out a de-identified data set. And he showed, first of all, and this isn't a concern with the IWPC data because nobody's really worried about their VCORC1 genotype, but he showed if somebody was in the training set, just by releasing a model learned from that data set, you gain insight into their VCORC1 genotype, which is very worrying, just releasing the model. Similarly, just releasing the ROC curve can release information. So as you vary this epsilon parameter that increases your privacy, what you see happening is you protect against disclosure of too much information, but by the time you've protected sufficiently, you've tanked your utility in terms of accuracy of the predictive model and clinical utility of the predictive model. So we think this is a very interesting research area to continue. How much can we improve things with technical approaches to privacy, and to what extent does this have to come down to policy approaches to privacy? And finally, with GWAS, we're interested in getting more sensitive GWAS by essentially saying each of these hidden variables in a Markov network is whether or not this marker, this SNP, is really related to the disease, and what we have are just the statistical tests, the p-values of association with disease. But we know from HapMap and other sites the correlation structure among these SNPs, and Gia Liu has shown that this can improve your accuracy and your sensitivity in GWAS by taking that correlation structure into account with Markov network inference. So with that, here's just some mom and apple pie for conclusions. With that, I'll stop. Thank you.
Can I ask you a quick question before everyone leaves, just in kind of monitoring our progress in communications? How many folks are here from CMU today? Raise your hands. Score today. Okay. A lot of new faces here. So are most of the new faces from the Pitt campus then, I would assume? Anyone not Pitt here? Where are you from?
I'm visiting. I'm looking at going to school here. I'm from CDC.
Oh, congratulations. Okay. From Germany? Wow. Great. Okay, sorry.
Thank you for coming.
Sorry.
Anything else? Any questions?
David, why did you use in the latter work you talked about Markov networks rather than a directed graph?
Okay, it was because at least in our experience, we didn't feel like we learned the directions very accurately. We could learn the edges fairly accurately, but we were hit or miss on the directionality. So the Markov network was basically letting us avoid that source of error in our learning.
Okay. Right.
I guess the other piece I didn't mention was I mentioned CTBNs earlier. We're also very interested in whether you could train a CTBN and use the intensity parameters to get insight into some of these. If the drug is boosting the intensity parameter for a condition flipping from false to true, I think that may be an alternative approach to this as well. Yes?
So with your temporal model, your CTPN, can you, or what can you do about unknown relations or starter endpoints, which is going to be endemic if you're talking about symptoms from a clinical record?
Yeah.
Think about that?
Yeah. So that comes down to a pair of approaches, hoping that even with the noisy starting and ending points, and in fact the problem's worse because we almost never get ending points. Anyway, people don't come back and say, "Thank you, Maya." Yeah. And so we're hoping that we can make some initial guesses about starting and ending points and get a reasonable model, and then kind of in an EM-style fashion, bootstrap our way up. The problem is that requires a big inference problem. And so right now, I was mentioning computational issues. We can't scale our CTBN method up beyond 30 or 40 variables right now, and we'd like thousands. But we feel like with some improved particle filtering approaches, we can at least push that out a little bit and do inference better. If we can do inference well enough, we feel like we can, in EM style, hone in more and more accurately on the start and end points. But right now, we can't even do that experiment with reasonable numbers of variables. That's the big challenge. These are great questions. Thank you. Anything else?
There's one more. Quickly, I'm fairly trying to make it quick, but with causal discovery, if you find something new in terms of evaluating the EHR, a relationship that looks like a new adverse event for a drug, what are you going to do then? I know this is a bit of a loaded question, but you and I talked a little bit about this last night. But I still think it's an interesting one to.
Yeah. So if you see, one of the nice things is the FDA is nice for us anyway. As you guys know, the FDA is on the hook to try to follow up on these, and they need to have a way of prioritizing them. And so the simple answer is we're just viewing our job as to accurately rank these and hand them off to someone else. But other approaches we talked about are privacy becomes a big issue here. But getting access to other data sets and seeing if it holds up in other data sets. And then presumably if we can get some clinicians interested enough, you would take you would do some kind of or if you get approval, do some kind of prospective trial. And in the end, as you and I talked about, the best we can hope to do is propose mostly useful hypotheses in terms of causal connections, and then there has to be some type of follow-up to determine. Yeah.
Hi, I'm just curious to know some of the methods that you use for combining the clinical information and the genomic information, because you mentioned that when you combine both of them, your area under the curve decreases. So I'm just...
It doesn't increase, yeah, it doesn't significantly increase. So usually what we're doing, the most common approach is either based on the literature or based on an initial GWAS analysis that we do or that someone else has done. We will try to pare down the million SNPs to maybe 100 or 200 SNPs. And then we add those as another table. I showed you the relational database. We add those as another table, and the algorithm just uses that as another table. So it it can say if you're homozygous for this value, or if you're heterozygous, or it can do an overall allele count. If you have 1 or 2 A's at this position, then that becomes part of the rule as you're learning it. Or whatever learning algorithm you're using becomes one of the features to that algorithm.
All right, I want to thank David for an excellent lecture. I want to kind of tip the winds towards the collaborations we're trying to build with the University of Wisconsin. As part of our BD2K program, David's kindly agreed to join us as a scientific catalyst to help broadcast what we're doing to his colleagues at University of Wisconsin. And it sounds like he's got to check in with Mark Craven on this. Has agreed to actually host our first technical site visit. So David, this is Mike Davis. He's the guy I spoke to you about this morning that will be accompanying you when we make that visit. And the idea there is to create a white paper that would describe how our plans with CCD here in Pittsburgh could interface then with the computational phenotyping, predictive computational phenotyping center that they have in Wisconsin. And if you ever have a cause to be in Madison, please dial up David and his team. What they have going at the University of Wisconsin at a number of levels with their CTSA program, with access to a large data warehouse, and the collaboration, most importantly, with Marshfield Clinic, is something to really see and know of for potential collaborations. They really have a phenomenal thing going in Madison. So as an insider on their EAB for their CTSA and as an advisor to the Marshfield Clinic Genome Initiative, they really have something special going on in the state. They even have a public health network going out to dental clinics that are collecting oral health initiative data and SNPs and genomic and saliva samples. Knowing that actually helped my sister get a job in a public health dental network because she lives in Wisconsin. So we've used this network very actively to do some pretty interesting things. But they've got an amazing opportunity in central Wisconsin with this partnership with Marshfield that folks should learn about.
Thank you.
Thanks, David.
Sir.
Their subject